shown. And we've been given an equation and we've been showing that the delta H here is exothermic. We might need that later on. It's a negative number. We're then being given some standard entropy values. Remember, entropy is the measure of the disorder. The bigger the number, the more disordered. So we can see these are all gases, and we can see that nitrogen monoxide has the highest disorder. We're being asked to calculate the entropy change. And the entropy change is the sum of the entropies of the products minus the sum of the entropies of the reactants. And I'm bearing in mind that these are per mole quantities, so we will need to take account of these molar quantities in the equation. So we're going to start with the products. We've got 4 lots of 211 and 6 lots of 189. And then we're going to subtract the sum of, so that's why we've got the big brackets, so 4 lots of 193 and 5 lots of 205. So we need to type all that in our calculator, trying to keep the rules of BODMAS, so making sure that we're paying attention to the brackets. If we don't use those big brackets, then we need to apply in that second bracket that minus a plus becomes a negative. And if you do that correctly, you should get positive 181, and there'll be no units marked for units because we are just adding and subtracting. That's why they've given us, they are just the units from the table. Remember, this is a double page spread, so we can see both parts at the same time. It wants us to calculate the Gibbs free energy change in kilojoules. We have to pay attention to that because remember the units are important. So we need to remember that delta G is delta H minus T delta S. We were just given the delta H back up here at the beginning as minus 905. So we got minus 905. Now the temperature 600 degrees C is in the wrong units. Remember, units are so important. So 600 plus 273 equals 873 Kelvin. So it's going to become 873. And then our 181 that we calculated, but remember that the units are important. We need to go into kilojoules, and ours was just in joules. So we're going to divide it by 1,000 or times 10 to the minus 3. Now if we do that and we pop that in our calculator, what we should find is that we're getting a large negative. My calculator's given me minus 1063.013. I'm just going to round that. And they've given all their numbers to 3 significant figures, so I'm going to round that to minus 1060. That's my answer. The reaction between ammonia and oxygen was carried out at a higher temperature. Explain how this would affect the delta G for our reaction. So if we look at where temperature is in our equation, so remember in our equation was going delta G equals minus 905 minus our temperature times 181 times 10 to the minus 3. Now it's a negative number, and if we make the temperature bigger, we're going to subtract more. So we're starting off at minus 905 on our number line. So it's like, imagine 0 up here and we're down here at minus 905. And then we're subtracting our T delta S, which is a positive number, but we're subtracting it. So we're getting more negative, and the bigger the temperature, the more negative this number will become. So delta G becomes more negative. Yeah. Because, should probably say it as, T delta S gets bigger. The next part of the question is actually not from thermodynamics, more from transition metals. Transition metals, the section on catalysis. Platinum acts as a heterogeneous catalyst, so that's given us a clue. It's a different state to the reactants between ammonia. So these were gases, and platinum is a solid. How does this solid provide an alternate route with lower activation energy? So it's asking you to remember those 3 sort of key features of heterogeneous catalysis, which is that the reactants, so this would be the ammonia and the oxygen, adsorb, that means they stick onto the platinum surface, so the solid surface. Bonds in our ammonia and our oxygen weaken, then break. And new bonds form. And this is the alternate route of lower activation energy. Because they're stuck to the surface, this weakening takes less energy. This weakening means less energy is needed, and so we've got an alternate pathway of lower activation energy. And then our products desorb or leave the surface. These 3 bullet points should be clearly in your notes for the sort of mode of action of heterogeneous catalysis. Deduce the change in oxidation state. So always hydrogens are +1. So we've got 3 +1s. So nitrogen is -3. And then here oxygen is -2 and nitrogen is therefore +2. So it's going to increase from -3 to +2. And then it says when ammonia, NH3, reacts with oxygen, N2O can be produced instead of NO. So let's have a look. We've got ammonia and oxygen, and then we're going to go to N2O. And we're going to have a look. Now we've got some hydrogens still to go, and the top tip is if you're unsure, it's usually going to be water that balances an equation. But let's have a look at this. We're going to definitely need to put 2 in front of the ammonia because we've got 2 nitrogens in N2O. That's going to give us 6 hydrogens, so I think we need to have 3 waters over here to balance that. Now if we add up the oxygens, we've got 4 oxygens on the right in total, so 2 O2s will give us 4 oxygens on the left.